I'm going to start this tutorial with these three photos. You're probably familiar with the picture on top, but you might not know that the other two pictures are also of computers. The woman on the bottom left is Katherine Johnson, who is this genius mathematician who worked at NASA during the 50s and 60s, and among other accomplishments, calculated the trajectory for the flight that put the first USian in space. The third photo is of a toy called the Digi-Comp II, and it's going to be the primary subject of this video. So let's take a closer look. The Digi-Comp II kind of reminds me of a pinball machine, but it's actually a really large-scale mechanical calculator. The original was built in the 1960s, but the version you'll see in this tutorial was made by Evil Mad Scientists, who have graciously allowed me to use their image and video content. The way you use the Digi-Comp II is you set certain pieces of the board in a particular initial state, and then let those metal balls at the top run through various channels down the board until you've completed the calculation you set up, at which point you can read the result of that calculation in one section of the board, called the accumulator register. If you've never seen something like this before, you might be wondering, how is that even possible? So let's start by taking a look at the board in action. In this example, the board is set up to multiply 5 times 9. There's a few things to notice about the setup. The multiply switch is set to on. The multiplier register is given an initial value of 5 in binary. And the memory register is given an initial value of 9, also in binary. Once the board is set up, the calculation is initiated by someone pulling the start lever at the bottom, which releases the first ball from the input guide at the top. Over the next couple of minutes, you can see the balls from the input guide travel down the board through various trajectories, coming to rest in the repository at the bottom. Notice that the path each ball follows depends on the arrangement of various switches, whose orientation can in turn be changed by the passage of the balls. Also notice that each ball presses the start lever again as it completes its trajectory, initiating the journey of the next ball. Towards the end of the video, you can see that the calculation is able to stop itself when it completes by sending the last ball down the squiggly path on the far left, where it doesn't intersect with the start lever. We'll come back to how that happens later. At the moment, you may be getting a general idea of how this works, but you may be confused about the details. What controls the trajectory of the balls? How does the calculator know when to stop? And how does this procedure manage to calculate the product of 5 and 9? To answer these questions, we'll first need to take a little detour and talk about binary. So, to binary. Binary can be confusing at first, because when we learn math in school, we tend to take for granted our particular decimal number system, which uses the 10 unique symbols displayed here in every possible combination to represent every possible number. Make a string of 1 and 2 and you get 12. Make a string of 7, 5, and 4 and you get 754, and so on. You can represent any real positive whole number you want in this fashion. Most of the time we assume that this is just how numbers are. You count up to 9, and then you put a 1 in the tens place and a 0 in the ones place and move along. But the reality is that decimal is just one of many possible systems. To think about this, start by imagining a number system in which you had a unique character to represent every single number. Imagine the apple at the top of this page represents 1, and the banana next to it 2, and so on through the donut in the bottom right corner is 24, and subsequent numbers as their own unique symbols. Imagine that these symbols never repeat, but just continue being unique forever, no matter how high the count becomes. This system would be pretty terrible for everyday math, since calculations would become difficult. How would you know what pepper plus pizza equaled other than by memorization? So decimal makes a lot more sense for our purposes. But decimal isn't the only system that makes sense. Consider the two systems displayed here. Instead of using 10 unique characters or digits, the top system shown here only uses 7. That means that once you've finished counting to 6, you've already run out of unique symbols, so you need to start using 2 digits to represent subsequent numbers. What looks to our eyes like the number 10, that is, the 1 digit followed by the 0 digit, here represents a number with the value 7. 2 ones strung together represent the value 8, and so on. In the bottom system, we use 13 unique symbols, meaning we don't need to use 2 digits to represent a number until we hit the value 13. What looks like 10 here is actually 13. If this is a bit confusing, feel free to pause the video here and spend a little more time thinking about these two systems before moving on. I promised this detour was going to be about binary, so let's talk about that. Binary is just another system like the ones we've been considering, only with binary, you only get 2 unique symbols. So you have to start using 2 symbols or digits once you count past the number 1. The digit 1 strung together with the digit 0 therefore has a value of 2 instead of the value 10. Thus this joke. When we're using the decimal system, we speak of there being a ones place, a tens place, a hundreds place, etc. In binary, we instead have a ones, twos, fours, and eights place, and so on, because the values 2, 4, 8, 16, etc. mark the points when we need an additional digit to represent the next counting number. Since in binary, any given digit in a number can only have 2 values, it's the perfect system for doing math by stringing together components that can be in one of 2 states, like on and off, or full and empty, or left and right. Each state represents a digit of 0 or 1, and stringing the components together lets you create numbers. All of which brings us back to the Digi-Comp II, which does exactly that. It stores binary numbers with a string of physical components in 3 places. The first place is in the multiplier register on the left. This register has 3 components that are switches, meaning they can point left to 1 or right to 0. That gives us 3 digits, or up to the number 111, aka 7. This is where we store the smaller of the 2 numbers we're multiplying together using the Digi-Comp II. The second place is the memory register, which has 4 switches. It can hold a number as big as 1111, or 15. This is where we store the larger of the 2 numbers we're multiplying together. Finally, there is the accumulator, which has 7 switches, meaning it can hold up to the number 1111111, or 127. The accumulator is where the final value calculated by the Digi-Comp II will be stored. Now that we have a little more context, let's watch the Digi-Comp II perform the example calculation more carefully to see how it works. As we noted before, in this example, the Digi-Comp II is multiplying 5 by 9. Notice that what the multiple switch does when on is direct the balls to the left into the path of 3 other switches that we'll talk about in a moment. Since 5 is the smaller of the 2 numbers we're multiplying, we place it in the multiplier register on the left. Notice the switches are pointing at 1 in the ones place, 0 in the twos place, and 1 in the fours place. We can understand this just the way we understand the number 356 in decimal as 3 hundreds, 5 tens, and 6 ones. In this case, 1 4, 0 twos, and 1 1 comes to 5. Now we want to put the 9 in the memory register. Here we have a 1 in the ones place, 0s in the twos and fours places, and a 1 in the eights place. That's 8 ones and 1 1, or 9. The accumulator, where we will be storing the result of our calculation, naturally starts with all switches pointing to 0. And now we're ready to start, which we do by pressing the start lever and releasing the first ball. The first thing the ball does is pass through this collection of switches at the top. Notice that as the ball passes through the first switch, it is directed to the left while at the same time flipping the switch. This sets up the switch so that the next ball that reaches it will be directed to the right while flipping the switch in turn. And so the balls alternate directions as they pass through this switch. The first, third, fifth balls, and so on, are directed left, and the second, fourth, sixth balls, and so on, are directed right. This pattern repeats when balls pass through the 2 switches just below. The first ball to hit each will be directed left, the second right, and so on. But each of these switches only sees half of the total balls, because only every other ball gets directed toward each. As a result, a quarter of the balls end up going down this left-left path. A quarter of the balls go down this right-left path. A quarter of the balls go down this left-right path. And a quarter of the balls go down this right-right path. So why does this matter? Well, as this process directs each ball along one of these four paths, that ball can accomplish some step in the calculation. What's more, the balls traverse these paths in the same order over and over again. You can think of each set of four balls traversals as a cycle. We'll talk about what happens during each cycle and why. To get there, we have to first talk about each of these paths. The left-right option, that is, when the ball takes a left at the first fork, then a right at the second, directs the ball along this path, where because of the configuration of the memory, the ball just falls into a hole without changing anything else on the board. From there, it takes a tunnel path down to the bottom, where it presses the start lever and releases the next ball. Notice that if the memory register were configured differently, in other words, if we were multiplying 5 by a different number, then it would change this path. For example, if the circled switch were set at 1 instead of 0, this path would send the ball into the accumulator register. The right-left option, where the ball takes a right at the first fork and then a left at the second, is similar. It leads the ball to another hole, again without it changing anything else on the board. But again, this is dependent on the arrangement of the switches in the memory register, aka what number is configured there. In this particular problem, when the ball takes one of those two paths, the contribution it's making to the calculation is simply to reconfigure these forks, so that the next ball can take one of the other two paths. The right-right path in this problem is a little more interesting. If the ball takes a right and then another right, it enters the accumulator register, the place on the board where we will eventually see the result of this calculation. As the ball passes through the top switch in the accumulator register, it flips it from 0 to 1. In the process, it gets redirected off to the right, where it makes its way down to the bottom and presses the start lever, thereby releasing another ball. But notice that the next ball to make its way along the right-right path and enter the count register then takes a left at this top switch. Making its way to the second switch, where it gets directed to the right and out of the way. In the process, it flips the top switch back to 0 and the next switch from 0 to 1. And this pattern gets repeated. Each time a ball comes through the accumulator register, it flips the top switch from either 0 to 1 or 1 to 0. And if it flips it to a 0, it then goes on to flip the next switch. And if that switch is being flipped from 1 to 0, then the ball gets directed onto the path of a third switch, and so on. So what's going on here? Well, it looks an awful lot like counting, right? The accumulator register starts with all 7 switches pointing towards 0 for a total of 0. The first time a ball comes through, it flips the first switch to 1 and gets out of the way, bringing the total to 1. The second time a ball comes through, it flips the first switch to 0 and carries the 1, switching the second switch to 1. This brings the total in the accumulator to 1, 0 in binary, which has a decimal value of 2. And this pattern will continue. Every time a ball comes through the right-right path, it will enter the accumulator register and increment the total there by 1. Okay, so we know what's happening in 3 of the 4 paths, but what about the left-left path? The left-left path is the most complicated path in this particular calculation because the balls that travel along it actually do 2 separate things. The first thing is something in this multiplier register, so let's take a look at that first. Remember that the multiplier register is initially set at 101, or 5. The first time a ball comes through, it'll hit the top switch and get directed off to the right, flipping the switch to 0 in the process. The second time a ball comes through, it will flip the first switch back to 1 as it's directed to the left, where it then travels to the second switch, flipping that switch to 1 and getting directed to the third switch, where it will flip it to 0. Are you noticing the pattern again? Something similar is happening here in the multiplier register to what was happening in the accumulator register. We're counting again, only here it's happening in reverse. Each time a ball comes through, we're decrementing the count in the multiplier register by 1. It starts at 101, or 5. After the first ball comes through, it reads 100, or 4. After the second ball, it's 011, or 3, and so on. Eventually, if enough balls pass through the multiplier register, its value will be equal to 0, with all 3 switches pointing to the right. Take a moment to think about what happens at that point. We'll come back to why it's significant in a bit. I mentioned earlier that a ball traveling along the left-left path performs 2 actions. The first we've seen is to decrement the value in the multiplier register. So what's the second? Well, you can see that after leaving the multiplier register, any given ball will end up on the path marked with a green arrow. From there, it will enter the lower portion of the accumulator register. Once there, it will follow a pattern we should be starting to find familiar. If the first switch that it hits is pointing to 0, it will flip that switch to 1 and escape the accumulator register. If the first switch that it hits is set to 1, then it will flip it to 0 and carry that 1 to the next switch, and so on. We're counting again, right? Well, sort of. Notice that we're starting not at the 1 switch at the top of the accumulator register, but at the switch marked with the brown arrow, labeled A4 on the board. To understand how that changes what's happening, consider how flipping A4 from 0 to 1 changes the value in the accumulator register. If the accumulator register were set to 0, flipping A4 from 0 to 1 would change the total value from 1000, aka 8. This A4, the 4th digit in the binary number, is the 8th digit. In the same way that incrementing the tens digit in decimal numbers increases the number's value by 10, incrementing the 8th digit in binary increases the number's value by 8. And because any ball that enters the accumulator at this digit is skipping all of the digits that came before, each ball that follows this path will increase the value in the accumulator by 8. Okay, so now we know that each ball that takes the left-left path decrements the multiplier register by 1 and increments the accumulator register, aka our total, by 8. We also know that the right-left path doesn't change any of the register values, but it does reconfigure the logic gate at the top. The left-right path behaves similarly, reconfiguring the logic gates at the top without changing the total in any register. We also know that the right-right path increments our accumulator register by 1. Finally, we know that these paths are traversed in a cycle: left-left, followed by right-left, followed by left-right, followed by right-right. So if we put all this knowledge together, we'll realize that each time we go through one of these cycles of 4 balls, the accumulator register is incremented by both 1 and 8 for a total of 9. And the multiplier register is decremented by 1. We're down to the final piece of the puzzle. Remember when I asked you to think about when the value of the multiplier register got to 0? Well, at that point, with all the multiplier register switches pointing to 0, the ball will have a clear path through the multiplier register without getting directed toward the accumulator register at all. It'll pass right through this winding path on the far left, skipping the start lever and becoming the last ball of our calculation. Notice that at this point, the cycle has repeated itself a total of 5 times. That's a total of 5 cycles, each of which has incremented our accumulator register by 9. Sound familiar? That's our multiplication problem, 5 times 9. And looking at our accumulator register, we see that it does indeed read 0101101, or 45, the product of 5 and 9. So congratulations, we made it! Now that we've walked through how the Digi-Comp II solved this multiplication problem, a good exercise would be to think through how changing the value in the memory register, say from 9 to 11, would change the calculation process. When you figured that out, think about how you could use the Digi-Comp II to solve a subtraction or division problem. A big thank you to Evil Mad Genius for letting me use their photos and footage in this tutorial. Please see the description for links to their pages. And thank you for watching this video.